Hello, everyone, and thanks for coming to our seminar today. In today's seminar, we are going to have a talk about automatization and telemetry in geotechnical performance monitoring. So this talk will introduce participants to the current real-world implementation of automation and telemetry, remote instrumentation with respect to the performance management of large geotechnical structures. As companies move towards database decision-making, this presentation seeks to explain the process used to extract, compile, and troubleshoot data coming from an automated geotechnical instrumentation system. Participants will be given an introduction to some real-world interface and systems that are used to manage fast response geotechnical instrumentation systems. Participants should leave with an head start in their understanding of some of the most valued on some after skills in the geotechnical engineering industry, as well as networking opportunities. So to do this speak today, we have with us Melissa Rudolf. She is a registered under the Alberta Professional Geologists Association as a professional engineer and holds a bachelor in civil engineering from the University of Alberta. Mr. Rudolf has 15 years of experience in the mining and oil sands industry and has spent the last 5 years as a governance leader on Suncor geotechnical strategy and close team. Primarily, spearhead its $5 million automation and telemetry initiative. She has a background in geotechnical design and performance monitoring of their dams and containment structure, mine waste dams, and pit walls. Her experience comes with a technical focus on instrumentation, data management, and digitalization, and processes and policy development. So please join me in welcoming Mr. Melissa.
Thanks, Daniel. I wanted to thank the University of Alberta for having me today to speak. Welcome back to another episode of PowerPoint Karaoke, as I figure out what is on the screen before you do. Just kidding. So thank you for that wonderful introduction, Daniel. I'm here today to speak about geotechnical engineering and the push towards automation and telemetry. I wanted to give, I guess, just a short background about me. I started working specifically in the oil sands industry in performance monitoring and geotechnical instrumentation things in 2008. And in 2009, the site that I was on, formerly known as the Albion Sands site, ran a proof of concept pilot project for remote instrumentation. They wanted to supplement their existing performance monitoring strategy with a fast response digital collection system, so that some of the more dangerous areas or more hazardous areas that the technical staff had to go to collect the data from vibrating wire piezometers and slope inclinometers, we'd be able to increase safety with that and ease the logistical pressure on having staff in place to do these readings. And since that time, I have been marinating in automated instrumentation data specifically. Ooh, I'm on mute. Would you like me to unmute myself?
Oh, you are mute.
Okay. Hi to everyone that is online. You've won today. My name is Melissa Rudolf, as Daniel so cordially introduced me. I've just told the room here that I've been marinating in instrumentation data since 2008 and automated data since 2009. And what I have noticed in this time is that there are actually differences in these at the surface level. When you investigate and you start to interpret instrumentation data, we're used to scrutinizing and verifying our data with certain questions. We ask, where is this data coming from? How is this data showing? And we can look at the trends coming in from our instrumentation, and we can determine whether it's valid or not, whether there's blunders or errors. And today I wanted to present to you an example of how automated instrumentation data is different and why we need to be aware of these things. These are the things that I want to cover today on this first slide. I'm going to walk you through an automation system. I'm going to speak about system design and considerations that we need to take when building an automated performance monitoring program. as well as industry integration of these programs and some of the keynotes moving forward. So, in terms of automation systems, companies keep telling us they are moving towards data-driven decisions. Data-driven decisions are going to inform and allow executives to make well-informed decisions. We do database research. Why shouldn't they make database decisions? One of the things about data-based decisions, though, is that the data has to be good. For everybody who's in the room right now, how often have you ever dealt with a vibrating wire piezometer? Fairly simple piece of equipment installed to measure pore pressure in fill structures and foundations. I wanted to run through an example of how I would scrutinize and validate data from a manual instrument and the same instrument once it is then automated. I wanted to present today VWP data because it is simple and straightforward. Essentially, for those who are unfamiliar, a vibrating wire piezometer is one of the simplest instruments that you can integrate into an automated system. When it is in the ground, the wires will output, there's a thermistor wire that outputs temperature, and there's a frequency wire that outputs what is called a B reading, which is frequency squared over 1,000. And that reading mixed with their calibration formula for each specific instrument will give you the real world engineering units that we like to review to assure ourselves that the field conditions that we see above ground are reflected in the ground. So what I presented here is some scrubbed data of two piezometers that I have named 5A and 5B. They exist in the same borehole, with piezometer 5A having been installed first and lower in the ground. There's also, so that is the yellow and the blue data points. The orange and green, unfortunately, my Excel has not popped this up. That is a different piezometer, piezometer 9. This is the type of data you might be used to seeing coming out of a manual instrument. We see a span of about 4 years on this chart, and these instruments have been read once a month. This has been, you can see, however, as we get closer to the end of the data in August of last year, there are some missing data points. One of the first questions that I would ask myself is, why is this data missing, and have I missed anything important? It is likely that they weren't able to access that data, or perhaps when somebody went to enter it, they got a computer error, and in dynamic mine site, for example, you may not have time to go back and fix that. You may not notice that because there are external pressures that do not allow you to necessarily get the most precise or accurate data in the field, even though it is present. Automation deals with a couple of those things. I want to take a look at the same data, but now as if it were automated. As you can see, there are far, far, far more data points, and you can see a lot more. The main difference between these two things is the sheer volume of data points that we can see. Number one, the first thing to notice about an automated system is that it can read as often as you want it to, or as little as you want it to. These systems in the industry were originally developed for remote applications. If you have to fly a helicopter out to take a reading once a month, it's going to cost you a fortune. If you hire a helicopter once and have your student install a system that can read itself and have that upload, connect via SIM or like via cellular or via Wi-Fi or whatever, and have that upload the data to you and to your computer, you don't have to take a helicopter out every month to get one single reading. You get better data, you get faster data, and you get data that fills out the ends a bit. That said, automated systems are built in such a way where you take this manual instrument and you essentially attach a data logger to it. So traditionally, where you would take the two wires coming out of the vibrating wire piezometer and plug them into an electronic readout provided by the vendor that would have provided the piezometer. You take your reading, you bring it back to the office, you input it into your laptop, into your database, and now you can plot the data. Every time we handle manual data, there is potential for human blunders, potential for human errors. And we're used to questioning that. When you see this data in chart format, you may see a typo and you may go, oh, okay, well, there's an issue there. And those are the questions that we're used to asking. Data loggers are the equipment that you install on a manual instrument that essentially takes that reading at whatever frequency you set it to. These specific piezometers were set to read 4 times a day, which sounds excessive, but if you have pore pressure changes due to drilling, or due to construction, it is very important, as you know, to monitor those. And the faster we can see a response and the faster that our systems can alert us to that, the better. That said, just because a logger is reading the instrument does not mean that that data is getting to you. This is the telemetric or remote communication aspect of it. These data loggers are set up on each individual piezometer, or sometimes multiple piezometers or multiple instruments can be trenched and then plugged into a single data logger. That data logger takes the readings at whatever required frequency, and then once a lower frequency, usually there is another system that we refer to as it's like a hub in a leaf or a node, and that hub is a connected communication system. It's got a modem, usually a cell modem, and that is how that data is uploaded. If the hub goes down, you may not see that data on your screen, but if you were to go to the field and investigate, their data logger should still be running, as those are independent power sources. So one of the issues that we have with this sort of setup in the field is that ideal conditions are not the same as our field conditions. It's hard to see here with the cyan, the blue data there, but in the middle here, what we have is, apologies. What we have here is something that got missed in the manual readings, because if we're taking readings once a month, we're only getting a point and we're interpolating that the data is the same between it's working its way up or down and the trend is the same. However, when you're taking this much data, you can notice errors like this, and they can be caused by just about anything. So having zoomed into this area, now we start to see, okay, there's been 2 or 3 readings in this time that are not what we would have expected. And in an automated system, the expectation that somebody would have while working in industry is that we would have set expected values and unexpected values as an envelope around our expected data. If you have enough data to essentially be able to predict what normal field conditions are like, you can set a program to alert you to when those field conditions appear to deviate. It's great because it means that even though we are still responsible for routinely checking our data and routinely reviewing our instrumentation data as it comes in, you cannot have eyes on it all the time. We have to sleep and eat, and we get weekends. And if I can get an email on a Sunday while the mine is still running that says, hey, something's not looking right, okay, well, I should go and pay attention to that. It's essentially just saying, hey, look at me. This envelope that I set here is for about 1.5 meters of piezometric head change. And as you can see, every single one of those points would have triggered an alert. One of the things that I caution people with when it comes to automated instrumentation is that you get desensitized very quickly. This is one piezometer we're looking at, and even over the span of 2 weeks, we got 1, 2, 3, 4, 5, 6 alerts where it would have gone out and then come back into range. And to immediately land on the conclusion that this is representative of the field conditions can be dangerous, because you can stop operations when perhaps you don't need to. So what I want to teach you today is how to scrutinize automation data, because these kinds of blunders, these aren't blunders, these are systemic errors, or these are errors that are due to where or how the system was built. So in automation as an amplifier, that is your number one, that is one of the takeaways I want you to walk away with today. We often think of automation as something that accelerates what we do. Hey, we can do it now, but faster. One of the analogies I like to use is essentially it's the difference between learning how to ride a bike and learning how to ride a motorcycle. If you have your basics down on balancing on a bike, motorcycle's gonna be a little bit easier. Lots of things are tougher, but also things can go horrendously wrong if you're not paying attention, and it does require a slightly different set of skills. I wanted to show you some erroneous data. This is the kind of error that you may get when you see automated data come in. And as I walk through how I would scrutinize this data, I'd like you to kind of have a think about how you would scrutinize this data. So this is a piezometer that I've named 12A. And as you can see, one day it just jumps. My first thought would be, well, what has caused, these are the readings, by the way. When you evaluate, when you see something a little weird, you get an alert from your system that says, hey, something's gone wrong. If you have set that value, or if you have set that alert to call you in when, if that alert is based on calculated values, like calculated engineering real world values, you need to be aware that something can go wrong in that calculation. And the thing that you should be evaluating is the raw data coming out of the instrument. So these are the B unit readings that are coming out. The first thing that I would think, if this was a manual instrument, would be, okay, something's jumped, something's not right. I don't know how this would have happened otherwise in a manual instrument, because this appears to me like the pore pressure increased significantly, but then it does also drop, or it does also drop off later, or it increases later depending on your curve. But I can see that after the change, there's data to support that that is in fact the new normal. That's not actually the case. The first thing I would do with automated instrumentation is take a look at that piezo number 12A. There's maybe a 12B. Let's look it up. Let's have a look and see what's happened here. If there's a 12B, it's going to give us a little bit more insight. When you put the 12B reading data in, now all of a sudden, and I apologize that the colors have populated as green and orange, but essentially at that point where the other data had ticked up, this data is now coming in and swapping down. And the trends look about the same. They're not identical, but they do follow the same trend. This to me indicates with the number of data points that something has happened in the field that is actually a fairly common occurrence when you are working under field pressure on a dynamic mine site. It is very likely somebody had to go out and fiddle with the logger or fiddle with or take a manual reading because they were checking something, or change the desiccant, or update the firmware, or do any one of these maintenance tasks that we often forget come with equipment. And when you install piezometers, I'm not sure how many of you have been on a drilling rig installing piezometers. These are issued in batches, and the serial numbers are not that different from one another. It could very well be that you have a serial number 96 and a serial number 64, and you can tell the difference, or you might get a serial number that is like 50, 55, and then one that is like, one that is 54 and one that is 45. And those two serial numbers are pretty close together. They can cause errors. This appears to me that logger that I was speaking about, where everything is plugged into a dedicated port, that someone has taken them out and put them back in the wrong way. This is something that would flag in your system, hey, please come take a look at me. And if you don't scrutinize this data and you immediately jump to the conclusion that this represents field conditions, you're going to make decisions, database decisions, but you're not making those decisions on good data. I wanted to highlight this because this is not something that would necessarily happen in your research, as you have a lot of control over how you're doing your research, and you are going to be detail oriented, and you are driven to get, like, your intent in getting data is to get good data so you can draw conclusions from it. Unfortunately, the pressures in industry are different. You've got 4,000 instruments to read, and some of them have gone a little bit, it's time to update the firmware. You send somebody out to update some of the firmware. They've got 18 of these things to do in a day, and something gets mixed up, but you don't notice it until later because the system's reading itself and you're not really looking at it if you're relying on it to call you in when there's an issue. That is something to be aware of. So essentially what has happened here, I wanted to give you a visual representation of what's occurred in that previous graph. What that previous graph is representing is essentially, this is what we've set up. This is what my contact list says in my phone for all intents and purposes. Your computer interface knows that whatever's coming in on this left-hand side is, it believes that it is piezometer 12B. And in the field, someone has gone, and what that indicates is that somebody has switched the wires, and your computer now believes that the data that is coming in from 12A, it is renaming as 12B data because you never told it you switched spots. If you guys switched offices and someone told me the person who is doing this specific research is sitting in office 104, I may go to 104 not knowing that, oh no, we've switched offices and I'm not that person. All I know is that if I have this thing I'm delivering to this office, not this person, same deal here. Your data that's coming in, your computer doesn't know. And with the amount of data that comes in, we end up with conflicting design intents for these systems. One of the reasons that we are pursuing automation is that it provides us with fast and frequent data. The ability to respond to changing site conditions is very important. It's great if you can do that from your desk. There's lots of benefits to that. There are also, unfortunately, some detriments. That data can be noisy, it can be inaccurate, there can be hidden errors if you don't know how to look for them. On the other hand, one of the reasons we also want to automate is we want to be able to present easier interpretation capabilities, faster interpretation capabilities, the problem that comes in is the data management. You can have, like you saw how many data points, how many hundreds of data points there were. You're taking 4 readings a day for several years. The site that was based on has 4,000 piezo's. That's one site. That gets very overwhelming very quickly in terms of your data storage. And when you are when you're trying to evaluate as a technical person, maybe I don't want to do it in the program. I actually want to like see my numbers. I'm going to run it through a spreadsheet. You're overwhelming that spreadsheet now. How do you make it a little bit more sparse so you can actually start to see trends, especially if you can see in the graph that there's some noise? We want to increase the signal to noise, and that can be a little bit difficult. It's also equipment that is fairly unfamiliar at this point in time because it is fairly new and it is constantly changing. So even from the time that I started with the project that data is from, in the last 5 years, a lot has changed. A lot has changed, and your legacy data isn't necessary. It's not necessarily backwards compatible as things change. As they add new features, your old data doesn't necessarily fit into the new model. One of the issues with data interpretation, live data interpretation as it comes into a system, is that the flexibility that awards us the ability to respond quickly is at odds with a stable database. Because in the field, you'll find that when you have a drilling program and you're installing multiple instruments, some people may find that writing, Silicon Valley Hill, Piezo 1, that's too many letters. I'm in a rush. I'm just gonna write SVH. That data is no longer queryable. That's now become, if it's not consistent, if somebody's added a space when they type in that name, you've now added issues into your database that you can no longer query. When you are searching for something and you forget to put in an extra space, maybe your system doesn't pick it up because it's not looking for an extra space. Or if someone has put in SVH, you're looking for SVH, turns out the instrument is named Silicon Valley Hill, you're never going to find it, especially in a pool full of thousands of instruments. So these are the two things that we need to be aware of when evaluating building systems. That fast and frequent data adds a lot of weight to your data interpretation and data management. But if we start to reduce the number of readings, we start to lose the benefit of automation, which is that we do get fast and frequent data. I will hop on this the day I die. Automation is an amplifier. You have the same number of eggs, you're just putting more eggs in fewer baskets. It makes your day-to-day tasks easier, but you must take the extra time that you have gained from that and put it into ensuring that those baskets are sturdy and robust. Because if you don't build a good system around automated data, you get bad data faster, which is not great. Moving back into that other point that companies are moving towards data-driven decisions. I wanted to talk a little bit about Industry 4.0 or Internet of Things. I'm not sure how familiar you guys are with this. Lots of the business consultants like McKinsey, et cetera, have encouraged companies to progress towards what is now being referred to as Industry 4.0. This is a system that we in tech have also referred to as the Internet of Things. This is the practice of using neural networks or artificial intelligence to start looking for connections between data points that we may not have put together as humans. You can take data from different groups and perhaps find connections that will give you an edge in business. This is a great idea. And when juxtaposed and put side by side adjacent to what we do in automated instrumentation works, it often gets confused with that. People are thinking that, hey, automated instrumentation, it sounds a lot like this Industry 4.0 thing. That is not the case. I think the simplest way to explain the Internet of Things is to say that in the same way that we may model our seepage through a computer model of our geotechnical structures, we're essentially, Industry 4.0 is attempting to make a digital model of the mine. The digital model of the mine is meant to now take inputs from several different places within several different databases from different groups within that corporation, so they can make better decisions. What we're doing informs this. So we do our work in geotechnical engineering, and we use this as a tool to feed into a database that then turns into a mirror of the mine in terms of a model. And that is the key takeaway. People may get confused here if you start talking to them about automation. It's not what they think it is. It is very difficult to have a shared vocabulary with an industry. And when you're talking about certain things and they're talking about certain things, you're actually referring to different things. I'm cautiously optimistic about AI neural networks. I think that there's a lot of really good things in the bones of this, but unfortunately, I don't think we're there yet. If you look at ChatGPT, for an example, an easy example, it's a language model. If you ask it to do a math question, a simple one, but a multiplication question, but maybe many, many, many digits, it does not, in fact, give you the right answer, even though a calculator can. What it does is it queries the language used in its data pool, and it will give you back the most likely next number that comes after the number it has previously calculated. So it's not quite doing what we expected to do. And I think it could. I think with the progress that we're making, we can get there, but I would caution you to dip your toe in before you jump in. And again, optimistic that it's going to work. We are not quite there yet. And I think there's an industry where we stand to benefit a lot. But the thing that we need to do is approach it cautiously. And one of the ways that we can do that is to ensure that we scrutinize our data. We're constantly scrutinizing our data. When it comes to automation, it helps you do good things faster, but it also takes bad things and makes them happen faster as well. Again, I only have, it's a pretty short chat, but I only have 3 major takeaways for you guys today. And I presume a lot of questions, and apologies for the casual passion I have for this. I could talk about this for days, so I'm trying to cut it down to the bare minimum for you guys so I don't bore you. But yes, top 3 things to remember. Number 1, companies are moving towards data-driven decisions. This is not something that we are going to be able to avoid. This is happening. It's now time that we move from an alarmist standpoint to an adaptive one. If you are going to be instrumentation focused in your work going forward, I would encourage you to scrutinize and learn how to recognize systemic errors in your data, because as they occur repeatedly, you may find yourself accidentally associating those errors as trends instead of what they are, which is systemic. If you are not going to be instrumentation focused, I recommend that you scrutinize your data and make sure you learn how to recognize systemic errors, or at least learn how to communicate with somebody who does, because the push is hard, and the change is coming from the top down. There's nothing that we can do about, there's no going back. And I don't think we should go back. I think we have a process that has a really good framework that can work really well and give us really good data that allows us to engineer within a smaller envelope and engineer better. And I'm not going to say less conservatively, but we can be more assured in our data because there's fewer blunders, but we do have to be aware, or at least be able to communicate with somebody who is aware of the pitfalls of this sort of instrumentation. Again and again and again, automation is an amplifier. If you have a good data collection system, if you have a good data collection process that is robust and has safety nets on how to, and if you have a very good intuitive understanding of how that data is collected and what that data should look like, and if you are very good at pattern recognition and can pick out where things are going wrong, this is going to be great. Unfortunately, we are tempted to think of automation as an accelerant and not an amplifier. We think, yeah, we'll just do this and it'll be the same, but faster. But we need to remember that systemic errors is cumulative. They will build on themselves over and over and over. And if you have ever used an Excel sheet where you've got something that calculates something, and then you just grab it and dump it over in another file because you want to calculate that same thing, and then you've got a whole bunch of reference errors, you need to understand what is going through this. Black boxes aren't great. It's kind of akin to learning how to drive a stick shift in a vehicle. An automatic vehicle is fantastic because it allows you to have the bandwidth to deal with your environment, deal with your conditions, understand those. But part of your environment is how that vehicle operates. And if you have ever had the pleasure of driving a standard or manual vehicle, you'll know that after time you do start getting used. It becomes almost second nature, where you can hear the engine, you can feel the engine, you know when to change gears, and having that knowledge when you apply that to an automatic system, you are going to be you're going to have a much better understanding than people from the outside looking in. And I think that will give you, I think that'll give you a real edge. I think it gives you a real edge if you understand that good data comes from good practice. It doesn't matter if your data is coming in from manual instruments that you are reading in the field or automated instruments in the field. Good data comes from good practice, and good practice is upheld by good process design. When you are looking to build a program that is bigger than just your research with a start and an end date, we're not talking about a project, we are talking about a long-term program where you're going to have, the program will outlast people. Because people are going to learn and then move around and change roles. That management of change starts to worry things. If you're building an automation program, I highly recommend that when you do so, that you account for the fact that people will need to be able to step in circumstances, not know anything, and then have very good documentation, as I'm sure you've been taught in coding classes, to have very good documentation in terms of what is happening, why it's happening, how to investigate it, and what it means, essentially. That's kind of all I had. It's a fairly short talk because I anticipated a lot of questions. I realized that I'm hoping that this wasn't too low level for you guys, but I find that we tend to think that we know a lot about this because it seems straightforward and simple. And once you have delved in deep into the data in the way that I have been over the last couple of decades, it becomes very apparent that there are things specific to this sort of data that no one has accounted for yet. And we are kind of at the precipice of this change, where I think maybe the class coming after you may be exposed to this sort of education, but as of yet, I haven't found any knowledge transfer from between this driver industry and these educational institutions where people are going to be dealing with this going forward. You guys are the next generation of engineers. And when you hit the field and you realize that what you've learned in terms of your class and your manual instruments and the data coming out of those is in fact skewed towards this, because this is happening at a large scale at many different companies right now. And you may not even have heard about any of this going on because there's no reason for it, because the people who are working on it, they're getting their job done, and they're moving on with the day. So I wanted to take some time to expose you to it at least, so you know what questions to ask. Thank you for your time. I really appreciate it.
Okay, now we have the time for the questions. So there is any question here in the room? Yeah, okay, so great.
My bugs.
Does scrutinizing your data and recognizing systematic errors come with a lot of practice, or can you just be like good at it right away? Because it seems like one of those things where it would kind of take time to really like learn.
I think it depends on the person. I think that's oh, sorry. Oh, my bad. Thank you, Daniel. So the question was scrutinizing your data or learning how to recognize these systemic errors. How long does it take to kind of learn those tasks? I frankly, in my experience, it has depended on the person and that person's learning style. Some people who are good at pattern recognition can take a glance at it and be like, oh, wait, that doesn't look right. And others need to experience it a couple of times to see what's happening and go through the process. And I've had at times 8, 9 windows open on a split screen. It looked like my minority report. I had 3 screens open, each of them with a slightly different piezometer from a slightly different area, trying to recognize what is happening. So some instruments are going to be more difficult than others. But harkening back to this, good data comes from good practice. If you understand the manual data very well, it will become a lot easier to pick out these errors in automated data, because you know what to expect now. When you look at a chart with manual data, you're like, this is the trend. I know what this is. And if you see perhaps like a small jump in piezometric elevation, your mind will be like, okay, that's reasonable. If you see a really big jump, that's a lot more recognizable as maybe not a manual instrument issue. Did that answer your question, or is that? It's good.
Any other question? Okay.
It's about the example of the size. So you think the concrete data would be more error and inaccurate,
Mhm.
and the fewer points would be more accurate and easy to explain with the next interpretation. So would that be considered a bad way? I mean, to just delete some data from the large size volume of data to a few points, then just pick some few points, be that be fine or do you have any comments?
That's a great question. I'll come back. I'll pick it up. That is a fantastic question. The question is, because it is easier to recognize when you have a little bit, your data is a little bit more sparse, can you not just go in and delete some points of data? You absolutely can. How are you going to do that for 4,000 instruments? How are you going to do that?
Maybe just
Select a timestamp. That's a fantastic idea. You've got manual readings in there now that aren't being taken every 6 hours. So if you're taking readings at 12 o'clock and 6 o'clock in the morning and the evening, you may have somebody go in and just to make sure things are working, and they've taken another reading, and now it's like 4:53 that they've taken a reading. How do you pick that out of an immense data set? That is the real question. So there are programs out there that can do this. It is a part of that desktop. It's a part of what these vendors for instrumentation. There's Bentley, there's Canary, there's RST's got Terra Insights and GeoExplorer, and there's lots of companies out there that do this work. They were all VDV View of Vista. That's Bentley now. Sorry, I apologize. There's a lot of programs that are built to be able to do exactly that thing. Manage that data on the back end on a server, and then you get to see and you can make like, okay, I just want to see every month. I just want to see every month. These were built to be able to accommodate our needs in geotechnical engineering, and so they don't do it in a very consistent way between systems, and they're not necessarily, it's not Google. We're not talking about a multi-billion-dollar company that has unlimited resources and unlimited data sources in order to teach the program to do these things. They are trying to help us in a fairly niche industry. Like, you've mentioned before, Danielle, that the geotechnical engineering world is pretty small. There's not a lot of us that do this. How can a company subsist itself with our work alone and accommodate that need? They need to simultaneously understand what we do, understand software engineering as well, and then develop something that works for that case. Now we have an added complexity where, again, a lot of these were built for remote. There's a lot more when you can apply this automated mindset and this automated system to construction, pipelines, dam monitoring, all of these things. Now, all of a sudden, what we need in mining, which is very dynamic with lots of changes, is in complete opposition to the set it and forget it system that they have there. I'm not saying it can't be done. You're absolutely right. You can just take the data out. But the data that I am talking about now is like gigabytes upon gigabytes of literally just numbers. And every borehole has 2 or 3 pieces in it, maybe, and then they are all over the place. How do you get that consistent? How do you pick out these errors? Automated problems require automated solutions, and we have to toss this on every level. That is absolutely one way to do it. Start pulling it out. Actually, how we built the manual data is essentially we did that. We brought it into an Excel sheet, filtered out everything except for the first of the month, and then deleted the rest of the data, which is great. It took 15-20 minutes, but I don't have 15-20 minutes times 4,000 to do that, which is unfortunate. And then if it takes you more than the 6 hours, you now have another set of readings that's come in over 4,000 instruments. And so if you do instrument ABC on day 1, and then on day 2, you've now done a different instrument, but you've now got data coming back into here. And so now every instrument has a different day that you've made that change, a static change. So we need to be able to understand that there needs to be a dynamic change. Some programs can do it, some can't. That's one of those problems that I would put it to you to solve. I don't have the solutions yet. I wish I did, but I'm really hoping that this is something that, with giving you guys an understanding of what challenges face us, that we'll be able to resolve in the future.
There are times where the instruments fail. So that means if the instrument fails, we may face the short of data during a bunch of time. And what should they do in that situation? In one instrument, or we just put something there to monitor?
Great. Okay, so my understanding of the question is, if the instrument fails, what do we do in terms of replacing the instrument and reinstalling, or like we just installed it. When you refer to the instrument, sort of this little nuance, when you refer to the instrument, are you speaking about, in this case, of the piezometer or the geotechnical instrument, or are you speaking about the logger failing? Because that can also fail. All of this stuff. Okay, so the answers are going to be different. Now, if your instrument fails and it is the instrument itself, the recommendation is essentially find the money to redrill that hole, because there's a reason you needed to install a piezometer there, because you need to know what the pore pressure is in that area, right? The reason that we install instruments is so that we understand what's happening in the subsurface. If that instrument breaks, the need to know what's happening underground doesn't go away. So you would reinstall and then move the data logger onto the new instrument and continue to take readings. And those you would not be able to necessarily, it's not advisable to conjoin the historical readings from your old instrument and the new one. Before you drill a new one though, you can attempt to repair a lot of these. If there's a fault in the cable, for example, where it's trenched or the connection, you can use a fault monitor to try to find out where it is, dig it up, splice it with some new wire. Usually these remedial activities take place before we drill again, because it can be very difficult to drill again. So most my answer, like I'm more than happy to, if I didn't understand the question, I'm more than happy to understand the question and actually answer it.
What I'm saying is, because those instrument failure, for example, sometimes that instrument failure, and it's not until we look at the data that we find this instrument have failed. So what should we do to avoid this from happening? That means to avoid to drill another hole to put another piezometer there. Yeah, that's my.
Okay. Yeah, so in that case, you would attempt to repair it. There's these are all electronic parts. Typically, if there is a failure, you're going to see a big jump or change in your data. That will likely alert you to what's happening. Sometimes there are occasions, this is tangentially related to what, so the answer to your question is attempt to repair it. Attempt to repair it before you drill another, because if you can fix it, you'll get much better data, and you'll just have a gap that you have to account for in your reporting and say, hey, instrument failed here, we've repaired it, just document why there's a gap. That said, if your logger goes down and you switch loggers, you now have to change everything in that communication line from that instrument into your systems that you can read it and understand in real world terms. Yeah, I think generally your system should be able to alert you if something does fail, and then you would have to go investigate in person, determine if it is, attempt to fix it. If not, you may have to redrill it. One of the there's one point that's just like hanging on the tip of my tongue and I can't quite remember, so maybe I'll move on. I'll jump back if I recall what it is. Are there any questions from online, Daniel?
No.
Okay.
Anyone here has any other question?
I see. No, so do you have a schedule? Do you have a schedule to maintain this plan, like to targeting any failure of the instrument or sensors, or you only to fix it when something fails?
That is a fantastic question. My understanding, again, just to confirm, is that do you have a maintenance plan in order to do preventative maintenance before the system fails? Yes, you absolutely should. There are things that we don't tend to consider when we build these things because we're geotechnical engineers. We care about the dirt, we care about our instruments, we expect these things to work. We forget that things that aren't attached to a computer have firmware. That's software that's installed on the loggers, that's software that's installed in the hub or the modem or the radio. And these things need to be updated. Campbell Scientific, for example, if you buy one of their loggers, they will send you updates on when there's firmware updates. I plan an annual, like I like to plan an annual, all right, these 3 days, everybody's going out and we're updating all of these because at some point they stop supporting that software. Same as your phone. If you don't update it, you're going to open yourself up to security risks and you're going to open yourself up to that software going out of date. So you should absolutely be doing preventative maintenance. One of the issues we run into in the field as well is that where the project that I've specifically worked on deeply have been in Fort McMurray, where it gets cold in the winter and where it gets dark in the winter. We can set alerts. I've set alerts before for batteries. So when the solar panel is not as effective because of the angle of the sun and the lack of time that the sun is in the sky, we can set an alert to, this harkens back to your question about the pieces, we can set an alert on the battery to say, hey, it's dropped below 12 volts. You have 2 days to basically get out there and replace this battery before you start losing data. So we can do it in a way that like we can actually prevent data loss in reacting or responding to changing conditions. But certainly, preventive maintenance, just like for your car, is the number one way to prevent issues happening in systems like this. Great question. Yeah. Wait, can we do online first? Okay.
A follow-up question. Sure. Is it common that an instrument fail because you mentioned that we have thousands of instruments and these are the based on different risks quite better? Minus 40 or something like this, you know.
When instruments fail?
Yeah. Is it a common thing?
It's a great question. It shouldn't be common. The instruments are built to remain so that we can get a consistent data set. Unfortunately, again, the sites that I have worked on have been fairly dynamic, which means that there's lots of things happening, there's lots of construction happening. It is incredibly important that we monitor when our urban structures when we are constructing because things change very quickly. But if that's the case, that means that there are bulldozers driving around, there are haul trucks driving around, there are graders driving around, and they can nick or stuff like that. If they, those are big, that's big equipment, and if they cut one of your cables by accident, because they do, that's an instance where I would consider that an instrument failure. But yeah, in terms of the actual instruments itself, it's fairly rare, but you may see things like Sarah and I this morning, we were talking about drift. Sometimes the thermistor in these piezometers will start to get a drift, and so your temperature readings from your data will start at 3 degrees and be like 3.4, 3.4, 3.5, 3.5, 3.6, and it never returns. It just keeps creeping up until it's hit the hundreds, and that's going to affect your data because if you are applying a correction for that temperature, you're now applying a cumulative kind of drift to it. That is also instrument failure, but the mitigation for that would be to just not apply that temperature correction or apply the seasonally accurate average that you have until now understood it to be, which is it's like being less precise or accurate more consistently. I don't recommend it. But yeah, hopefully the instrument should not drift so much. But yeah, I'm talking about like real world human error causing that. Answer your question? Sure.
It is kind of the opposite of this. Is when would you recommend or advise continuing with manual readings instead of do an automatization? I mean, automatization is great, but where is the limit, or in which data you said, look, in this one is better that somebody goes every month and take the data?
That is also a great question. You guys are full of great questions, eh? Like no one wants to know about what's your middle name, what's your mother's name. Nobody wants my credit card information. So that's a great question. At what point do you automate? At what point do you remain manual? There are some instances where if access is easy or if installing is cost prohibitive, if you need to, you can automate SIs, by the way, sloping kilometers. There are like in-place kilometers you can use. There's also Measurand now. RST has what's called an SAA. Basically, it's a bunch of tent poles that you shove down the compressed in the hole, and it will tell you the movement and upload your water and do all of these same things that we just discussed today with piezometer, but with a slope clinometer. They're expensive. Those are expensive. As soon as you get away from the piezometer stuff, it starts to get very expensive because again, it's very niche equipment. It may be cost prohibitive, especially if something is under construction and you have visual monitors on it day and night anyways. They can just take a reading and upload it because they have access to a laptop on site. That is very, very likely and probably best applied to the case-by-case basis, based on your understanding of what is whether the benefits outweigh the risks, right? Because again, it's not that automation, you can't automate away your problems. Automation, sometimes in very quickly changing conditions, is important because you can get faster data, but in something that is fairly stable, means you need to, it becomes a cost to benefit ratio kind of situation.
Do you think as automation becomes more common, those really expensive ones that are really niche will become less expensive and then they'll keep like exponentially becoming more common?
I do. That's a great question too. As we've seen with all technologies, first they start off being very expensive for a very few small critical cases, and then they become more ubiquitous. There was a time that I believed owning $1,000 phone would have made me rich, and that's not the case. We all have cell phones, but that doesn't necessarily mean that that it's not an indicator of anything anymore because they are ubiquitous. And so I would absolutely say that even in recent years, as it's become more prominent, that the access to that will increase. That said, technology also tends to progress at a pace that we can't necessarily keep up with. So the second that one thing becomes ubiquitous, you're going to have people doing very, very boutique specific work with a brand new thing that is about to become ubiquitous. And so you're constantly chasing this moving goalpost. And trying to keep up with it, but yeah. Even this stuff, like even again in 2008, 2009, there were no interfaces to look at your live data coming in from even a software that was being developed. Whereas now it's everywhere. You can find a vendor that will call you every 3 weeks just to make sure that you remember that they have this thing that does this, that does exactly what we do here. Yeah, so it kind of waterfalls the same way that like software technology does.
Okay, thank you very much for being here, and we are expecting to having you next week with our seminar. Yeah, thanks, Elisa, for being here. Yeah, this great talk. Just for the knowledge of everyone, you can pick up some gifts from here. The people that is online cannot. So the people that is here in the room, you can take those beautiful cups and everything that is here that I'm going to show in camera just for the people live in what they need.
Oh, thank you for having me, you guys. I appreciate it.
Oh.
Like, lanyards.
And there are more cups.
Yeah, that's all. Thank you very much and see you next week.
Thanks for having me.